You ever feel a gentle breeze on a warm day and think, how can this exact same thing, the wind, become powerful enough to knock down a tree? Well, what connects them is this invisible force that's, believe it or not, shaping our world every single day. So today, we're going to dig into the science of pressure, from something as simple as a push all the way up to the heart of a raging storm. Okay, let's get into it.
Yeah, the wind. We all know it. Most of the time, it's nothing, right? A welcome cool down. But then you see an image like this, and you remember that same gentle push has a totally different side, a pretty terrifying one. So, what is the difference? What turns a nice breeze into a force that can literally rip the roof off a house? I mean, where does that incredible energy even come from? It seems like a massive question, but the answer? Well, it starts with something surprisingly small. That's right. To really get a handle on the power that fuels a hurricane, we have to start with the kind of power you can generate with your own two hands. We're going to zoom way in from the scale of global weather down to something you can hold.
All right, let's start with a really basic action, just pushing on something. Seems simple, right? But it turns out how you push is just as important as how hard you push. Let's see what that actually looks like.
Okay, check this out. On the left, a hammer hits the nail's head, and that sharp point just slides right into the wood. Easy. But on the right, you flip that nail around and hit the sharp end, and it basically goes nowhere. Now here's the crazy part. The force from the hammer is exactly the same in both situations. So what gives? The force is identical, but the outcome couldn't be more different. I mean, why does one work perfectly while the other just fails? It all comes down to one single concept. And that concept is pressure. This is the secret sauce. It's the reason a sharp knife cuts and a dull one doesn't. It's the key to understanding that whole nail experiment. So here's the deal. Pressure is just the amount of force you apply divided by the area you apply it over. So think about it. If you take that same force from the hammer, but you concentrate it all onto that tiny, tiny tip of the nail, the pressure becomes massive. You've definitely felt this before. Think about a heavy backpack. If it has thin straps, they just dig into your shoulder, right? That's because all that weight, all that force, is focused on a really small area, creating high pressure. But wider straps? They spread that exact same force over a larger area, which means way less pressure and a much happier shoulder. And what's so cool is how universal this idea is. It doesn't matter if it's a high-tech backpack designer or someone using a simple rolled cloth to carry a heavy load. The physics is the same. Increase the area to decrease the pressure. It's genius, really. Okay, so we've got pressure down for solid objects, but this principle doesn't stop there. Now we're going to scale it way, way up. Because right now, you and me, we're basically living at the bottom of a giant, invisible ocean of air. Take a look at this little rubber sucker. When you press it flat, you're pushing all the air out from underneath it. But what's holding it down so tight? It's not glue, it's not some magic suction, it's the incredible weight of that entire ocean of air pressing down on it from the outside. And just how incredible is that weight? Well, get this. On a little square just 15 centimeters by 15 centimeters, the atmosphere is pushing down with a force equal to the weight of a 225-kilogram object. I mean, that is a huge amount of weight pressing on every single part of your body all the time. Which, leads to a pretty obvious question, right? If all that force is constantly pushing in on us from every direction, why don't we just, pop? And the answer is actually kind of beautiful. The air and the fluids inside our bodies are pushing outward with the exact same amount of pressure that the atmosphere is pushing inward. It's a perfect stalemate, a state of equilibrium that lets us walk around without ever even feeling this colossal weight. All right, so now we understand this idea of atmospheric pressure as this big, balanced force. So, what happens when we disturb that balance? Well, that's when you get movement. That is how wind is born. This super simple setup explains everything you need to know. The air in that big, full balloon is packed in tight. It's at a higher pressure. When you connect it to the smaller balloon, the air rushes out of that high-pressure zone and into the low-pressure one, trying to even things out. This right here is the golden rule of weather. Honestly, if you remember just one thing, make it this. Air always moves from a place of high pressure to a place of low pressure. Always. And the bigger that pressure difference is, the faster the air moves. We have a name for that movement. We call it wind. So, now that we have that golden rule in our back pocket, let's scale it up. Let's see how the atmosphere uses this exact principle to build something as wild and powerful as a thunderstorm.
It all starts with the sun. First, the sun heats up the ground, and that ground warms the layer of moist air right above it. Then, because warm air is lighter, it starts to rise, leaving behind a pocket of low pressure. And ding, 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 here comes our rule. Cooler, denser, high-pressure air from all around rushes in to fill that low-pressure gap. That's our wind. As all that moist air keeps rising, it cools, water vapor condenses into clouds, and eventually a huge discharge of static electricity gives us lightning. And just like that, you've got a thunderstorm. Okay, but what happens when you take that same thunderstorm engine and you put it over the most powerful fuel source on the planet, a warm tropical ocean? Well, that's when you get the ultimate weather machine, a cyclone.
It starts just like a thunderstorm, but on steroids. The warm ocean water makes the air rise super fast, creating an intense low-pressure zone. As all that water vapor rises and turns into clouds, it releases a tremendous amount of heat, which is like pouring gasoline on a fire. It just fuels the whole thing to go faster. This creates an even bigger low-pressure void, sucking in huge amounts of air from the high-pressure areas around it. And then, here's the final piece of the puzzle. The Earth's rotation starts to spin all that inrushing air, organizing it into a massive, swirling cyclone.
And this is the result. A truly colossal spinning engine made of wind and rain. It's a self-sustaining system, all built around a center of extremely low pressure. And that center is so calm and clear, we call it the eye of the storm. It's just a terrifyingly perfect example of our rule, air moving from high to low pressure, but on a planetary scale. So we've gone all the way from a simple push of a nail to the mind-boggling mechanics of a cyclone. And that core principle, air moving from high pressure to low, it explains it all. But it does leave us with one final, pretty urgent question. We get the physics, we know how these storms work, but as our climate continues to change, can we really predict what they're going to do next?